Okay, so this is the outline of chapter 33. So we'll introduce what is so-called electromagnetic wave, and then also introduce the Poynting vector, which describes how the energy is transferred through the EM wave, and then yes, some related stuff called radiation pressure, polarization, and then some other simple thing you may have studied in the primary, high school physics class. It's like reflection, refraction, total internal reflection, polarization, something like that. Okay, so first, just so here it says what is electromagnetic wave. So in the Bible, if you're Christian, no matter Protestant or Catholic, you may know you may have studied the Bible, or maybe not. You might still know what is a Bible. So so in Genesis, Genesis is supposed to be the first book of the Bible. So Genesis, the first chapter, first to third verses. So this is actually the NIV New International Version. Okay, so actually, in Cantonese it's like 起初神創造天地，地是空虛混沌啊，淵面黑暗，神的靈魂行在水面上。神說有光就有了光。Okay, so it really means that in the beginning, God tried to create the world. So at the very beginning, the world before he create the world, there is nothing in the world, but actually there are some waters. Before he created the world, there are actually some water. And the first thing he tried to create is the light in the first day, according to what the Bible said. So the first day he created light. Okay, so if you Christian, then this is how we have the electromagnetic wave. So let's go back to the science point of view. Okay, so I think in chapter 21 we may have introduced something similar, which is called a Maxwell rainbow, which means that usually what we know about rainbow is like according to the visible light, we can see red, orange, yellow up to the purple. Okay, so in that case, this is a rainbow in common sense. But actually, if we consider the Maxwell rainbow, which is actually related to the EM wave, so for this rainbow in the visible light, it is only a small part. It only occupies a small part of the Maxwell rainbow. So actually here you can see here we have two axes. One is called frequency, 频率, and the other axis is called wavelength, 波长. And of course, this wavelength and frequency have a relationship like C equals F times lambda. F is the frequency, lambda is the wavelength. So F and lambda are inversely proportional, and this is the speed of light. Speed of light. Okay, so if we have a higher frequency light, then its wavelength is shorter, and vice versa. So you can see on the very left side, this is low frequency, which means it has long wavelength, long lambda. And in this part, it is a high frequency. and then it has short lambda. Okay, so on the left side it is so-called the long wave. I don't know what it is, and then radio wave, starting from around here, radio wave. So if you listen to the Macau radio station, it is like a 100.7 megahertz. 100.7 megahertz. So mega is like 10 to the 6th power. So considering these two, it is like 10 to the 8th power. So which is around here. Is in the FM, frequency modulation. But this is not a communication course, so I don't try to explain on what is FM, what is AM. So here you can also see this is FM radio around here. And then AM radio slightly lower. Yeah. Yeah. And then for higher frequency, something around here, yeah, it is used for TV broadcasting. TV broadcasting, something like several hundreds of megahertz, or maybe starting from 54 megahertz to 862 megahertz. Around this, this is so-called VHF and UHF. It's around this frequency range used for transmitting TV signal. Yeah, my PhD research topic is related to this stuff, so I know that. Okay, so you can see here TV channels using this frequency range. And and here, if you try to go a bit higher, it might be used for something like the mobile communication, like 2G, 3G, 4G, 5G, yeah, maybe 5G, even higher. Okay, so for like several gigahertz, or maybe 1 gigahertz to like 3 gigahertz, mainly used for the mobile communication. Mobile communication, and also like Wi-Fi signal are like 2.4 gigahertz, 5 gigahertz. Yeah, so using this range of frequency. And for 5G, if you really need a high data rate, for the 5G communication, it will use around 30 gigahertz. More precisely, it's like 29 gigahertz. Okay, so you need to distinguish what is 5G, what is 5 gigahertz. I frequently listen to some of the people don't really distinguish what is 5G, what is 5 gigahertz. 5 gigahertz is not 5G. Someone will say like, the Wi-Fi using the 5G. No, that's not the same thing. The Wi-Fi using 5 gigahertz, maybe like 802.11n using the 5 gigahertz. This is a frequency band you are using. And for 5G communication, this G means the 5th generation. The 5th generation of communication. So in short form, it's called 5G. It's not 5 gigahertz. Okay, it actually using the frequency around 29 gigahertz. So for 29 gigahertz, or at least we can consider is a 30 gigahertz. Yeah, this is 10 to the 9th power. So this is around 3 times 10 to the 10th power, which is somewhere around here. Okay, so you can see the wavelength. The wavelength is shorter than 10 to the negative 2. 10 to the negative 2 is 1 centimeter. So this 10 to the negative 2 meter is like 1 centimeter. So here we are using something like the millimeter wave. So the millimeter wave. So when we talk about the 5G communication, sometimes we will mention something called millimeter wave, which means that the EM wave have a wavelength in the millimeter level, And as much as you would like to receive a signal with different wavelength, then your antenna should be have a similar dimension. Just say if you would like to receive a millimeter wave, then your antenna can be like millimeter level is okay. But for FM radio, this frequency is much lower, which means that the corresponding wavelength is very, very long. It's several meters. As you can see here, more than 1 meter. So in the past, when I was small, when we need to listen to the FM radio, then your radio is this large, and then the antenna is this long. You need to drag this the antenna of the radio, then you may be able to receive the signal. And even for mobile, when you need to listen to the radio, then you need to plug in the earphone. The line of the earphone is acting like the antenna. So if you don't plug in your earphone, then the mobile phone cannot receive the FM signal. Of course, you can receive the FM radio through internet, but this is two mechanism. If you really need to receive the FM radio in the air, then you need that earphone, the line of the earphone as the antenna. Okay. And then if we want to go further, then here is the visible light. Lower than, if the frequency is lower than a visible light, it is called infrared, 红外线. Okay, 红外线. And then higher than the visible light is the ultraviolet, 紫外线. So which means that the red light has the longest wavelength, and the violet has the shortest wavelength within the visible light. Or in other words, the red light have the lowest frequency, and the violets have the highest frequency within the visible light. Okay, if you move further, we have the X-ray and also the gamma ray. Just like I've mentioned last time, the magnetic field generated by the Earth are shielding us from the high energy particle to shield something like the gamma ray. And of course the X-ray are used for something like body check, to check whether your bone or your lung are healthy. And other equation other than this one you should be able to remember it. It's very helpful. And other one related to this Maxwell rainbow is like this one. E equals HF or H nu, depends on what symbol you would like to use. Although we will not teach quantum mechanics in this chapter, but at least I hope you know this is actually the energy of a photon. Okay, so this is proportional to the frequency. This factor is called the Planck constant, which I have introduced in the slide of chapter 32. So this is called the Planck constant. Multiply the frequency. So if frequency is higher, the energy per photon will be larger. That's why on the right side is so-called the high energy particle, high energy photon. And for this side, the energy is low. Okay, so it says in mid 18th century, I mean 19th century, mid 19th century. Okay, visible infrared ultraviolet from the light were only EM wave known. Okay, at that time they don't know other EM wave. Okay, so later on, Maxwell's work, however, Hertz, okay, this guy called Hertz. So we know Hertz because this name is used for the SI unit of the frequency. So we know this Hertz discovered what now called radio wave. At the same and verify that they move through the lab at the same speed as a visible light. It's a speed visible light. Including they have the same basic nature as visible light. And then we know the widest spectrum of the EM wave as a Maxwell rainbow. So so Maxwell is a great physician. He actually unified the electromagnetism as the Maxwell equation. And then based on the Maxwell equation, he can derive the wave equation. Get the wave equation from the Maxwell equation. And then by solving this wave equation, he can predict the existence of the EM wave based on mathematics. Of course, he don't really do the experiment to verify that those things are EM wave. At that time, only visible light, infrared, and ultraviolet are known as the EM wave. And later on, Hertz, based on this theory, to use some experiment to find out really it is really some EM wave other than these three types of EM wave exists in the world. And he also verified that the EM wave has the same speed as the visible light. Okay, so finally we really know the Maxwell rainbow. Okay, so here it trying to let you know how we can really generate the EM wave with some equipment. Okay, so first of all, we have some energy source. It provides some, like a battery to store some energy here. Or maybe we have a circuit, and then as much as we have some current, a time-dependent current charging this RLC circuit. So in chapter 31, if we have an RLC circuit and then we provide some sinusoidal source, then here we will have a oscillation with the same frequency. Okay, so in this sense, this L will have a current, of course, and as much as it has current, it also has energy generate, which means that it try to convert some energy in the electrical form. And then here is a transformer. So this transformer will transform this energy to this part with a transmission line. Then this is an antenna, tangent. So with the antenna, and of course there are some current. We have some I secondary, I primary, and then also we will have I secondary going through this part. And as much as we have some current flowing into this antenna, and you can imagine, as much as we have some partial I, partial T, or maybe we have some, if we have some changing current, then there will be some partial phi E, partial T over some region of near the antenna. Then it will generate something like B field. time-varying B field. And then the time-varying B field, according to the Faraday's, according to the Faraday's law, Faraday's law, according to the Ampere's law, it will generate the changing E field, and then going back to here. So it will generate the EM wave like this. Okay, which means that we can have some energy source through an RLC and then with a transformer, and then this power is transferred to the antenna. Then this antenna will generate the EM wave, and then EM wave will carry this energy to far away. And then maybe you have another antenna. You have another antenna outside, then it can receive the power. That's how the wireless communication works. And here you can see this curvy line is the wave front. Is the wave front of the EM wave. These are the wave front. So it's like you drop a stone into the lake, then there will be some wave front moving forward. But if we just consider this point to be very, very far away, then we can just consider this is a plane. And then finally, we will make this assumption called the plane wave, which makes the calculation much easier. If we need to consider the EM wave near the antenna, it is called the near field. Then it will be a bit messy. But if we consider the far field, actually I should have mentioned the far field before when we talk about the electric dipole, something like that. We sometimes will assume that Z is much larger than the dimension of the dipole. Then the expression will be easier. So here, similar things occur for the EM wave. When we consider this point is far away, then even though it is still a sphere, but here we actually place this antenna head here. So the EM wave for the antenna will be like a plane wave. Okay, so this is an arrangement for generating the traveling EM wave in the shortwave region. And then the LC oscillator produces sinusoidal current in the antenna. And then P is the distance point at which a detector can monitor the wave traveling past it. Okay, so maybe let's stop here today, and then